I will shortly address the topic of quantum sensing, then I want to talk about what nonlinear interferometers are, and then I want to give you an idea about the quantum Fourier transform infrared spectrometer which we built in our group. So when we speak about quantum sensing, it's a wide field. So in most talks you will usually have systems which are atom-based or solid-state-based, as we heard it in the previous talk. But there's also photonic quantum sensing that we can take specially prepared photonic states, being it photon pairs or being it squeezed light, and use it for different types of application. And I want to give you one example for the usage of photon pairs for quantum sensing. Yeah, so what's normally done is you prepare a state with whatever system with whatever state which has transitions, and then you observe the development of the state over time and use it as a good sensor. When we speak about quantum sensing with photons, so there are two key questions. So the one thing is, so what is the best spatial resolution, for example, which we can achieve? Is there a chance to break the diffraction limit, and what are the smallest detectable signal changes? Can I beat the shot noise limit, and so on and so on? And the picture here are just illustrations for those two cases. What I'm going to talk about later on will deal with the second one, because we're speaking about a spectrometer. So our workhorse are photon pairs, which are usually produced via spontaneous parametric down conversion in nonlinear optical crystals. I do not want to go into detail how we do that. The conversion efficiency is very small because it's spontaneous processes, but as you will see, even if the few photons we can generate via spontaneous parametric down conversion can be a very, very powerful tool. In the spontaneous parametric down conversion, we are generating photon pairs, and we have strong anti-correlation in terms of energy and momentum because of energy conservation and momentum conservation. And in addition to that, we have a very strong time correlation and spatial correlation when we produce those pairs. And I will show you in the next steps how we can build interferometers using those photon pairs. But for that, I just want to make a short detour into the classical interferometer, where we split a light beam into two parts. Can be different ways like Mach-Zehnder or Michelson or whatever you have, and then we recombine the beams, and we can measure phase differences between the two parts. The amplitude or the degree of visibility can tell us something about whether the interferometer is balanced or not, and all that what's used in classical interferometers for measurement purposes can also be done in those nonlinear interferometers. So, and then of course the question comes, so what is a nonlinear interferometer? And we will go through it step by step to look at all the building blocks. So the first building block is that we have one of those nonlinear optical crystals where we generate the photon pairs. One photon is called the signal, the other one is called the idler. But we don't limit ourselves to just one crystal, but we have a second crystal which gets pumped from the same laser source, which generates signal and idler photons again. And since it's spontaneous processes in both, it means we're having two thermal or two stochastic sources. So at the moment, at that point, there is no connection between the two sources. But the interesting thing happens is when we build an interferometer out of it in the way that we take, for example, but it's not limited to it, the idler photons from the first process and couple it into the second crystal. Yeah. And then we combine the two signal photons or the two signal beams via a beam splitter on a certain detector, and then there is a very interesting thing happening. If I now, for example, move that beam splitter here, as a function of displacement, I would see interference contrast for the signal photons. Yeah? So we have two originally independent sources, but the fact that we are coupling in at least the idler beam into the second crystal leads to a fact which was in the early 90s called induced coherence without induced emission, that this coupling here via a purely quantum effect leads to the generation of this type of interference. Yeah? You can also look at it in this way. Some people prefer, when they look at interference, to ask the which way question. Yeah? If I do the perfect alignment of the two crystals and all the beams for the signal photons, I would not be able to tell whether a signal photon came from the first and the second crystal. And as long as I cannot answer the which way question, I would expect to have interference. So why is it of interest for us? Of course, I emphasized the connection between the first and the second crystal via the idler beam. If we block that idler beam, then there is no interference any longer, because, of course, for the signal photons, I cannot tell which way they came, but since I generated pairs, I can transfer that which way question to detecting the idler photons, and every idler photon I see here, it's clear it must come from the second crystal because I blocked the way between the first and the second. Yeah? So just as a very basic thing, how that principle works. So and this basic concept was developed, as you can see, already like more than 30 years ago, but it was considered for a long time a purely scholarly or academic point. But there are good chances for applications, because it tells me that since signal and idler photon are so strongly correlated, and I can see in the interference pattern of the signal photon what happened to the idler photons here, I can use that concept to transfer information from the idler beam to the signal beam. But of course, as long as signal and idler photons have the same wavelengths, this may not be interesting. But spontaneous parametric down conversion gives us, for example, the chance to generate photons far away from degeneracy. So, for example, I have one visible photon and I have one photon in the mid-infrared. Yeah? So I can make my idler photon talk to my sample, and I can make my signal photon carry the information to a simple standard silicon detector. Yeah? And that is what those nonlinear interferometers do. And let's say the potential which we have is, for example, that we can take information from the terahertz range, from the mid-infrared range, and also from the UV range via those photon pairs and do the detection or do the imaging, for example. For imaging, it's even more crucial. Do that in the range where we have really good detectors and cameras. And this picture here comes from a Fraunhofer internal project, which did run from 2017 until 2021, where we developed several different implementations of those nonlinear interferometers to see what it can be used for. Yeah, it could be used for microscopy, could be used for gas analysis, but it could also be used for film thickness measurement via some kind of tomography and stuff like this. So I'm going to speak about the infrared range, and there is a strong motivation to build such a nonlinear interferometer for the infrared range. And the reason, one essential reason, are infrared detectors, especially when you look at cameras. What this plot here shows is a really technical one. It shows the so-called specific detectivity. That's how good an infrared detector can be as a function of the infrared wavelengths. And this D star is a critical number, and you see that's a logarithmic scale. And this purple line here, that's silicon, which has a perfect, as we would say, as mid-infrared people, detectability. And the longer you go into the infrared, the worse the performance of those detectors are, because for an infrared quantum detector, to detect the photons, your band gap has to be smaller and smaller and smaller, which makes the chance for dark currents and dark signals larger and larger. Yeah? And that's our motivation to say, okay, so we can do that type of work distribution between one infrared photon interacting with the sample and one visible or near-infrared photon which carries the information to a silicon detector. Before coming to our own implementation, I want to give you a short information that, of course, we were not the first one. We were not the first one working on those nonlinear interferometers away from degeneracy. So the key work came from the group from Anton Seilinger in 2014, where they did imaging using 800 nanometer photons and 1500 nanometer photons. Yeah, not surprisingly, of course, it was a cat which they put into their mask, paying tribute to Schrödinger. Then we had the group of Krivitsky in Singapore. He gave the very first demonstration that you can indeed measure the infrared spectrum of a gas using that type of concept. But I would like you to pay attention to that length scale here, 3.8 micrometer to 4.6 micrometer. And what you see here is a strongly broadened and not really nicely structured image of the carbon dioxide spectrum. And then a group in Berlin of Sven Ramelow, they did the first demonstration of doing optical coherence tomography using the same type of concept. I want to shortly come back to the work from the Singapore group, which was the very first work on detecting gases. So their interferometer looked very simple. You had the first nonlinear crystal, the second nonlinear crystal, you had the generation of the photons in the first, the generation of the photons in the second, and only the signal photons made it to the spectrograph to record the data. The infrared, the idler beam, or the idler photons were blocked, and in the space between the two crystals, you just filled as much as possible carbon dioxide in to get a nice signal. And you get such interference fringes as you expected in an interferometer. Here is the wavelength axis of the signal photons, and you see for a certain operation range, you have a narrow wavelength range, and then you can observe the interference fringes from the overlapping of the first and signal beams. And by looking at how the pattern looks like with and without sample, you can then deduce the spectrum. So every data point was a single measurement for setting the conversion condition in the crystal to a separate point. The spatial resolution was relatively poor, but it was a demonstration of principle. I just want to show that here because I want to use it as some kinds of reference to what we finally did in our measurement. So one, of course, needs the interference fringes because the visibility of the interference tells me something about how many of the idler photons did get lost on the way from the first to the second crystal. That means how many idler photons had been absorbed. Yeah? So the amplitude information for the spectrum is contained in the visibility contrast of the interferogram. And if I want to measure a spectrum, I need to know the wavelengths of the photons, and that's what they use the spectrograph for. But we used a different approach. We said, okay, if I want to get these interference contrasts, for example, in a Michelson interferometer, like this one here, then I can use a different approach. Just to introduce a setup, the pump laser pumps a nonlinear crystal in one direction. All beams are collected. Then the infrared part is down here, where we can put a sample in. Pump and signal go in a separate arm, and now I would have to move the mirror here to observe those interference fringes on my single pixel photo detector here. And then we said, okay, if I have to move the mirror to get my interference fringes, why can't I just borrow the concept of the Fourier transform spectrometer that I move my mirror all the long way, record an interferogram, and from that get the full spectral information? And that is what we did. So the big step, so to say, was a small step by putting the mirror not just on a small piezo which jiggles the mirror by a few micrometer, but which allows to have a free movement of the mirror of about 20 millimeter, and then operate the whole thing really like a kind of like a classical Fourier transform spectrometer. Yeah. So the idler mirror is moved, but since the way how the photons here are generated in the second crystal depends on the phase both of signal and idler, we get the complete information. Yeah. So this is how an interference pattern looks like, more or less like in a classical Fourier transform spectrometer. And if you Fourier transform that, that is the source of our parametric down conversion, which is rather broadband from, that's about 4 micrometer and that's about 3 micrometer. It's the wave number range. And well, those fluctuations up here, you see it's not noise. It's a stable behavior of the parametric conversion process in the crystal. And when you look carefully here, those lines which you see here, we will look at them in more detail. That's the spectrum of methane which has been put into the optical path of the sample. Yeah. And that is how a spectrum looks like if we now put even two gases into our gas cell. That's a small amount of nitrous oxide, and that's a small amount of carbon of methane. And please look at the transmission scale here. That's 85% transmission, though we can nicely record the spectra of the two of them. And since our spectral resolution, like in an FTIR, only depends on how far we move the mirror, we can even achieve sub-wave number spectral resolution, which is required to record the methane spectrum in such a nice fashion as it's here the case. Of course, coming from an institute which does a lot of trace gas analysis with quantum cascade lasers and FTIR, we wanted to compare our data with modeling from the databases. So here you see the methane spectrum and the residues up here. For N2O, there is a stronger deviation as it looks like on the first glance, but please look at the transmission scale. Well, that's 100% transmission, that's 98 and 96% transmission, and the lines are still reproduced in a very nice fashion. And we set the concentration for our sample, and the concentration which we fitted have even, from the numerical fit, less uncertainty than the set concentration. Yeah. So it's possible to use those nonlinear interferometers to really build a spectrometer which allows to look at infrared gas spectra with high resolution. And in terms of signal-to-noise ratio, of course, we did not beat the classical Fourier transform people yet. I mean, Brucker is working on that for 50 or 60 years, and we just started with that, but we have quite nice features and performance already. Yeah. So I hope I could give you an introductory idea that using nonlinear interferometers based on spontaneous parametric down conversion and the quantum mechanical induced coherence without induced emission to do broadband spectroscopy here with a high spectral resolution which is required for gas analysis. And what are we going to do to that with that? Oops. So that's our quantum FTIR as it's operating in the lab. You see here the spectrum, which you could see already before, of N2O and methane. Of course, we will develop it in the direction of having application-specific features for spectroscopy. But what we expect, where the impact will be even bigger, is that we do hyperspectral imaging, where the question is not that I just replace one single mid-infrared detector by one single silicon detector, but where I replace an infrared camera by a silicon or InGaAs-based camera, and there are works underway to do hyperspectral imaging working on that concept, and the same thing may also be applied for optical coherence tomography. So with this, I want to give you a short introduction into that relatively exotic field here at this meeting, and I'm looking forward to your questions.
So is there a spectral limitation down to lower frequencies?
Well, the question was whether there is a spectral limitation towards infrared wavelengths, you mean, yeah. Of course, we are strongly dependent on the crystal in which we can do the spontaneous parametric down conversion. So at the moment we are using lithium niobate, though there it's more or less over at 4.2, 4.5 micrometer, but there are other groups in Japan and in Singapore who used other crystals, silver gallium sulfide, silver gallium selenide, where it's not possible to use the Fourier transform approach, but the classical one, which I showed you before, where you use a spectrometer, and they did it also nicely in the what the chemists call the fingerprint range between 7 and 10 micrometer. Yeah. The challenges are bigger because lithium niobate, it's really, if you can use lithium niobate, you have advantages, yeah, because they are far developed, they allow us to have broadband emission, which I didn't explain here in detail.
cancer detection, for example? How is the penetration levels?
Okay, yeah. Well, the question was about OCT. Can it, for example, be used for biological applications? The focus will most likely be not in biological applications, because when you go into the mid-infrared and you use regular tissue, it contains water, which is going to absorb your infrared radiation. So that's a strong limitation. Yeah? And also in our imaging, this will not be like living tissue, but you really have to prepare the sample in such a way that they don't contain water. Yeah? So we have the chance to collect the spectral information through the functional groups of different molecules which play a role in the functioning of the cells. But as long as there is water in, that's a general problem. So for the OCT, we expect the application to be more in technical applications, where the advantage is that the longer your wavelength is, the less scattering you have. Yeah, so like one example is you want to do tomography of buried structures in ceramics. Yeah, ceramics are a very nice candidate for scattering, and when you go to 3 micron, when you go to 4 micron, your penetration depth is so much larger. Yeah.
Are there any requirements for the pump laser in terms of coherence length or power?
Yeah. The question was whether there are any requirements in terms of, for the pump laser in terms of coherence, length and power. Well, for the power is the more the better, because the number of down-converted photons you have scales with the pump power. What we did, I didn't go into that in detail, although I should have done it for our setup. It's not shown in this. It's not shown in this scheme, but we demonstrated that we can do a pump enhancement for the conversion process. Yeah, it has a little bit extra of. You have to stabilize a resonator to the pump laser, for example, but that's more or less easily done, and then you get a sufficient enhancement. But of course, a powerful pump laser helps, but if you want to make a system for the field, like the one which I showed on the optical table, which operates with a 100 milliwatt pump laser, and you still get sufficient photon numbers. Coherence length or coherence in general matters in that respect, because I mentioned earlier that we have the energy and momentum conservation, and this is the key for transforming. So I measure the interference fringes in the visible, but what I want to observe is in the infrared. So, and when my coherence length is really poor, let's assume I would use a pulsed laser, I would get very nice photon numbers. But if the pump laser has a spectral width of, let's say, 10 nanometer, my spectral resolution of the measurement will never be better than 10 nanometer. Yeah? So in our attempt to go sub-wave number, well, that's the unit which the gas spectroscopists use, or at 3 micron is sub-1 nanometer, you really have to have a laser which is narrow line width and stable. When you do the resonance enhancement, then for the pump, this also has the requirements for the laser stability. I mean, you always have to pay a price. Yeah? The price for the pump laser, or the amount of work you have to do the stabilization. Things are interconnected, but there are sufficiently good lasers available which have, like, let's say, 100 milliwatt pump power, and which are narrow and frequency stable enough, and then it's gonna work. Yeah. So if the pump laser would start drifting, we do see it in our gas spectra. So even if it drifts only by a few gigahertz, we see it in our spectra, because of course we know at what infrared wavelengths the gas absorption lines have to show up. And then you find out displacements very easily, which in fact are not such displacements. Okay. Okay, if there are no further questions, thank you for your attention, and thank you for the questions.